So what we're going to talk about in this final chapter is hypothesis testing, and sort of what all of this has been building up toward is how you can use statistics to try to make predictions about things that might happen and how confident you will be that those outcomes could happen. So we've talked about confidence intervals before. We've done stuff with sample proportions, and we've used that to generate a confidence interval for the proportion. And instead of proportions, you could also have an average. So you could have X bar or mu as opposed to P hat and P, but it's a very similar kind of process. So first, let's look at some just sort of terminology and concepts about hypothesis testing. So hypothesis is a claim of some parameter, and a hypothesis test is going to be to determine how valid it is to make claims about that parameter. We need to have two hypotheses if we're going to do a hypothesis test. One of them is called the null hypothesis, and the other is called the alternative hypothesis. The thing that's a little weird about statistics is you're actually not going to try to find evidence that something's true. You're instead going to see if you fail to find evidence that something is false, which is a slight difference, but that's kind of the idea. So the null hypothesis, it's H0. That's what we are going to start with always. And so the null hypothesis is basically the assumption that there is no difference. Think of zero meaning nothing. It means there's no difference between the sample proportion and the population proportion. There's no difference between the sample mean and the population mean that you have. As an alternative, what you're actually trying to show is what you will phrase in your alternative hypothesis. And so that's what you're trying to find evidence for. If you're trying to see if a candidate has greater than 52% support, you would have HA be that it's greater than 52%, and the null hypothesis is that it's just going to equal whatever value you have. So we're going to calculate something called a test statistic, which we're going to compute using the calculator. A test statistic will fall in a rejection region, and if you fall into the rejection region, that basically means that you reject the null hypothesis. So again, the other thing that's a little weird about statistics is that rejection is actually kind of a good thing. So if you reject H0, that means kind of indirectly you were sort of proven right, not exactly. If you reject that there's no difference, that suggests that there is in fact a difference like you hypothesized in your alternative hypothesis. So the kind of general process that you'll have some given population proportion or mean. The question will be, is it different in some way? Are they just not equal? Is one greater? Is one smaller? And then to answer, we're going to be given some population proportion or some sample mean, some sample proportion or a sample mean. And we're going to see what the probability is that the sample is drawn, assuming these things are true about the population. So you're going to calculate a p-value. If the p-value is low, that means you reject, and that basically means there's a low probability. This is just happening by random chance. It's with it, there's a low probability that it's just sort of the general fluctuation you might expect to see. The difference is large enough that it's a meaningful difference. Okay. So the first thing you do is you make a statement or claim. you formulate the hypotheses, then you would, if you're a practicing statistician, you'd actually go out and collect some data. We're just going to have data given to us. You then analyze your data to see how believable the statement is, make a decision. Do you accept? Do you reject? And then you would then state in plain English what your conclusion is. So you don't just say, yep, I rejected my null hypothesis. Well, I mean, like, what does that mean? Like, to normal people, like, what is that? Okay. So the null hypothesis is always a statement of equality. It should always include an equal sign. And then you basically have three possibilities for the alternative hypothesis. Either the mu is not equal to mu 0. So that's going to be what's called a two-tailed test in your rejection region. There's actually a rejection region on either side of the bell curve. So either it's way too low or it's way too high. If it's equal versus less than, that's a left-tailed test. So if the alternative hypothesis is less, you're going to have a left-tailed test. Less is less. Your rejection region is on the left. If you have greater, that's a right-tailed test, so your rejection region's on the right. The alternative hypothesis is on the right. So here are some null hypotheses. So researchers want to know if it's reasonable to claim that the average age for a certain population is 45. So they would test these hypotheses. So H0, you would say mu equals 45. There's no stipulation about we want it to be greater or we want it to be less. So we just say either it's equal or it's not equal. So that would be what this would look like. Mu is not equal to 45. A company produces ball bearings which have a mean diameter of 5 millimeters. After replacing some parts in the production line, the lead engineer suspects that the diameters of the ball bearings are now too large. To test this, here's what you're going to do. So the null hypothesis is that it's just equal to the population mean, which should be 5. Since the engineer suspects they're too large, it's going to be a greater than statement. So we're going to say for the HA, the alternative hypothesis, mu is going to be greater than 5. The car manufacturer advertises that some compact models get at least 47 miles per gallon. And so maybe we'll change the phrasing of this, that they get, should really be less than 47 miles per gallon. The way that's worded is a little misleading. So anyway, if you're going to make a test for that, you would say either mu equals 47 or mu is less than 47. Because if it's less than, you're going to have a less than statement. We have a pollster that claims that greater than 40 or more than 40% of all people are registered as Democrats. So we would say our sample proportion is P equals 0.4. If we're saying more than, we're going to have P greater than 0.4. So during the process of a hypothesis test, H0 is the one that's tested directly, and there's two possible conclusions. Either you reject, or technically speaking, you fail to reject. So you could say you accept the alternative hypothesis, but strictly speaking, you're failing to find evidence that it's true, which is not quite the same thing. But anyway, so you either reject H0 or you fail to reject H0. Those are the two possible outcomes. Now, there's two kinds of errors that you can run into. If H0 is true, but you don't reject it, well, that's good, because accepting H0 is a good thing to do when it's actually true. Meanwhile, if H0 is false and you reject it, it's also correct to get to decide that yes, because I reject it and it's false, that's a good thing to do. Now you can have two kinds of errors. The first is a type 2 error, or one of them is a type 2 error, which is not as maybe problematic, but it's still an issue that you can run into. You do not reject H0, but H0 is false. So this is essentially like having a false positive. So like you don't actually have a medical condition, but you were given a test and it's a false positive. You might freak out a little bit, but since everything is in fact really okay, you're not that worse off than you were before. So that's a type 2 error, which is the idea, again, of like a false positive. A type 1 error is really bad. So you reject H0, but H0 is in fact true. This basically means you actually have like some condition, and when you go to test for it, they didn't find anything, and then it's just going to keep getting worse because you think everything's fine and you don't do anything about it. That's a type 1 error. And the reason it's type 1 is because that's, as I just suggested, that's the more problematic of the two in real world terms. But those are the two kinds of errors that you can have. So when we conduct a hypothesis test, we're particularly interested in the probability that we have made a type 1 error. So we're going to call that the level of significance. And we use the Greek letter alpha to denote the level of significance. The level of significance should be a small probability. You frankly could pick any one that you want, but the kind of standard ones that are used most in real world practice are either 0.10, 0.05, or 0.01. So either a 10%, 5%, or 1% chance that this will happen. Alpha you could think of as a threshold for what we're going to view as unlikely. So if we're going to use an alpha of 0.05, any event whose probability of occurring is under 5%, we're going to call that an unlikely outcome. So then we're going to have the observed significance level, that's the p-value. And so this is the probability of observing the value of the test compared to the null hypothesis that we have. So we're going to test a claim about a sample proportion, and we calculate the sample proportion. After we calculate it, we determine the probability of drawing a sample that actually gives us that proportion. And if it's far enough away from the null hypothesis, that's going to be in the rejection region. That's going to be a low p-value because it's so far away, it's very unlikely that it's just like the normal fluctuations. You know, you think of temperatures, you know, at a certain time of year in some place other than St. Louis where it's like 80 degrees one day and then 40 degrees the next. That like literally happened this week. But anyway, in most places where the weather is maybe a little more stable, let's just say, you know, there's kind of an ordinary range that the values can fluctuate in. And what you're trying to find is a value that's so far out from the kind of normal range that the probability of being that far away is really low. And so because that probability is low, you're going to reject your null hypothesis because that's clearly not a good like frame of reference of where the standard range should be, because you've gotten a value that's way the heck over here. And you should not be having a value that low based on where you think the population mean or proportion is actually located. So anyway, the smaller p is, the more likely we are to reject H0 in favor of HA. Here's how I'd sum it up. If P is low, reject HO. Just remember that. If P is low, reject HO. So when we're doing a hypothesis test, we're going to choose our hypothesis, conduct our test, assuming that the null hypothesis is true, but we're going to look for evidence to support the alternative. We decide on a level of significance, and smaller alpha values are sort of the cutoff. The small alpha values are considered the cutoff for what's unlikely versus what's just ordinary fluctuation in the data. And then we draw a sample and calculate the sample statistics. After we do that, we find the probability to see how far away the sample statistic is. And if it's super far away, that gives us a p-value, and if it's super far away, the p-value will be very low. So if p-value is smaller than alpha, that means that it's unlikely, and so we reject when p is low. If the p-value is greater than alpha, we do not reject the null hypothesis. And we're not claiming that the null hypothesis is true, it's just we failed to find evidence that it was false. So here, if we were to calculate that alpha is less than 0.05, what we would say is that H0 is rejected. So then we would say our conclusion, something along the lines of, there is sufficient evidence at the 0.05 level to conclude that the mean is greater than 10 feet, or at a 0.05 level of significance, we reject HO in favor of HA, that the population mean is greater than 10 feet. Suppose we calculate a p-value that is larger than 0.05, so then the sample evidence indicates that the null hypothesis H0 should not be rejected. So that basically means that there is not evidence at a 0.05 level to say that the mean is greater than 10 feet. So at a 0.05 level, we cannot conclude anything. Again, if you fail to reject, that doesn't necessarily mean the null hypothesis is true. It's just you don't have enough evidence to reject it. And so you don't really know what the outcome is. You'd have to try again. Come on, computer. It's thinking. All right, you ready? Here we go. So, hypothesis tests for population proportion. So we're going to work with two probabilities that are both often called P. So to try to minimize confusion, we're going to call prop for the population proportion. And P will be the actual p-value that we'll use for the hypothesis test itself. So, so again, always pick H0 so that prop is equal to P0. The alternative hypothesis will be some statement that prop is either larger than P0, smaller than P0, or not equal to P0. So you basically have three alternatives. You can have prop not equal to P0, prop less than, prop greater than. Notice that every single time H0, the prop is equal to P0. The population proportion equals the calculated P0 from the sample, the proportion from the sample. All right, so the way we do hypothesis tests, we're going to go to stat, arrow over to tests, and we're going to do a one prop Z test. We're going to enter the values of P0, X, and N, and then select the alternative hypothesis. Either we're going to say it's not equal, less than, or greater than, and then hit enter. So here we go. Before a series of debates, a candidate in an upcoming election is believed to have an approval rating of 37%. After the debates, his campaign organizer believes his approval rating is increased. The campaign conducts a poll of 560 likely voters. 225 of them say they approve the candidate. So calculate the sample proportion P hat. So P hat is just going to be the number of people who said yes out of the number of people who were surveyed in total. So that's going to be 225 out of 560. Let's see what that is. 225 divided by 560 is 0.4018. So it says clearly state the hypotheses of the test. Now, when I have graded exams on this, I have had lots of students write me very extensively worded and mildly paraphrased essays restating the scenario of the problem, and that is not what we are looking for. Here's what you do to state the hypotheses of the test. That means something very specific. It means, here we go. You say H0. H0 is always a statement of equality. So you're going to say prop equals P0. That is the null hypothesis. And then you do the alternative, HA. This is going to be some statement of either greater than, less than, or not equal. So we're going to say prop. What are we contending here? The campaign organizer believes the approval rating has increased. So guess what, my friends? If it's increased, that means it is greater than P0. So when you have a question that says state the hypotheses of the test, you're not writing me an essay in English reiterating the scenario that you just read. It means something very specific. You say H0 and some statement of equality. And you say HA and some statement that's either less than, greater than, or not equal. That's it. Those are the hypotheses right there. That's your answer. I'm going to put it in a box just for good measure. So when you do this kind of stuff on a test, that is what I should see. Capiche? All right, calculate the p-value of the test. So the prop, by the way, that we're comparing, the value for the sample proportion or the population proportion is 37%. That's what prop is. All right, so let's see, here we go. So we're going to go to stat. We're going to go over to tests, and we're going to do the one prop Z test. There it is right there, number 5. What is P0? I misled you all. I said that was prop. That is not prop. That is P0. Sorry. P0, that's 0.37. All right, so 0.37. Boom, here we go. Let's see, X, that is this, 225. N is 560. The 225 is X. And let's see, what is that? That's 560. Okay, so the proportion, are we not equal, less than, or are we greater than? Let's see what we chose here. Greater than. So we're going to arrow, it's actually already highlighted. If it wasn't, you'd arrow over to it. You did enter and select it. If you go over to a different one and hit enter, it selects a different one. But the one we want's over here, so we're going to hit push enter and do that. We're doing it in blue apparently, and we're going to calculate. There you go. You have a Z value. You have a P. You have a P hat. This is the P hat we found earlier, by the way. What we're interested in is the P value, 0.0596. That is the probability. So the P value is 0.0596. All right. So the question is, do we accept or reject? Well, that depends on the significance level that you pick. So again, just to reiterate, P was, what is it, 0.0596. All right, that's not what I want. 0.0596. There we go. So alpha is 0.10. That's, no. Highlighter. Boom. Thank you. Would we reject it? So P is less than 0.10. So guess what? In this case, you would reject H0. If P is low, reject HO. So you reject HO, which is another way of saying you were kind of sort of successful in what you were wanting to do, which seems kind of weird because normally we think rejection is a bad thing. All right, so then they say in layman's terms, state the implications of your decision. So we would say at a 0.10 level, we reject HO, meaning the approval rating did increase, or something along those lines, meaning the approval increased. That's what we're looking for. When it says stated in layman's terms, this is where you actually can write me a couple of sentences in plain English actually stating what the results are. Would we reject H0 at alpha of 0.05? Here's where things kind of get interesting. So in this case, P is actually greater than 0.05. 0.0596, which is a lot closer, which is really close to just 0.06. Guess what, my friends? That's actually bigger than 0.05. So then that would mean you fail to reject H0. Which is another way of saying you failed to find evidence. If you fail to reject, you fail to find evidence at the point evidence at the 0.05 level of an increase in approval. This is partly where when people make fun of statistics, and there's like the joke about how there are lies, damn lies, and statistics, this is kind of where that unfortunate stereotype comes from, because statistics are only good as the assumptions that you are making. And there's another adage about what happens when you assume that I will not repeat in polite company. But so let's just imagine you have a politician who likes to hear good news, and you're the pollster for this statistician, and so you could say, are you going to tell them that there's no evidence that their approval rating increased? Or can you pick a different level of significance and say, you know what? Oh, look at that. Now we can magically say, yes, your approval rating is going up. Isn't that amazing, boss? And the boss is going to be happy, and it may not bear much relation to reality, but there's a long, proud history of yes men and people telling people what they like to hear. So there you go. So it all depends on the level of significance you choose. And it's the exact same outcome, but depending on what you're going to decide is your level of significance, that's going to have an impact on how you report the results. Now, again, a good statistician will try to make as abundantly clear as possible, when statisticians are kind of notorious for really hedging their bets and being very cautious in the kinds of things they say. And people who report news on polls in the media often get hyperventilate over like a 1% change in like a candidate's approval rating. But statistically, that means nothing. It's meaningless. But anyway, it all depends on what you're choosing. And this is not wrong. You can choose a 10% level of significance. You can choose a 5% level of significance. It's just that you're telling your readers, or you're telling the people that you're reporting to how confident you are. If you have a 10% level of significance, that means you're 90% confident. If you have a 5% level of significance, you're 95% confident. So it just all depends. It all depends. Let's do another example here. A botanist has produced a new variety of hybrid wheat that he believes is better able to withstand drought than other varieties. They know that for the parent plants, the proportion of seeds absorbing water is 80%. All right, so this right here is going to be P0. So we know P0 equals 0.80. That's P0 right there. Let's see. The proportion germinating is unknown, but they claim it's greater than 80%. So emphasis on the greater than. To test this claim, you have 400 seeds. That's your N. 335 germinated. So that is your X. So P hat is going to be X over N. 335 over 400. All right, let's find out what that is. That's 0.8375. All right, so that's P hat. Clearly state the hypotheses. Again, that means something very specific in statistics. Don't write me a novel just rehashing what's in the scenario. All right, H0. We're going to say the prop equals P0. It is always a statement of equality. Always, always, always. The 0 means there's no difference. Zero difference, which is another way of saying they're equal. HA, they say greater than, so we're going to say, okay, that means prop needs to be greater than P0. All right, let's calculate the p-value, shall we? Break out the calculator, go to stat, head over to tests, go down to a 1 prop z test. Again, it's a prop since we're doing proportions, so we're doing a proportion test. 1 prop z test. This time P0 was 0.80. What was the X? It was 335. What's the N? It is 400. Again, we've got one where it's greater than, so you want to make sure that the one with the greater than sign is highlighted. You go ahead and calculate this, and you get a p-value of 0.0304. So that is P. 0.0304. Boom. There's your p-value. Now, would we reject at the alpha of 0.05? So again, let's see here. P was 0.0, what was it? 0.0304. Okay, would we reject at that level? So P is going to be less than 0.05. So when P is low, reject HO. So you reject HO. And so what that means is at the 0.05 level, we found evidence that what is it? The rate is, what is this? The germination is greater. We found evidence that germination rate is greater. Okay, there you go. In layman's terms, that's what we found. Would we reject at the 0.01 level of significance? Well, here, P is actually greater than 0.01, which means you fail to reject. And so if you fail to reject, that means you failed to find evidence. So at 0.01 level, you fail to find evidence of a greater rate. Fail to find evidence of a greater rate. Because that's what we were trying to prove in the first place, that the germination rate was improved, or that it was higher for this new strain of wheat. Okay, so that is hypothesis testing for sample proportions. We're going to do something similar for sample means. A lot of this process is going to be the same, but there will be a few added little twists to it that we'll get to when we get to the final section. See you all then.